Welcome. All right. Thanks everybody for coming out. This is, of course, DataWorks 2024. It is absolutely wonderful to see this many people at our short course this morning. Yes, exactly. Woohoo! My name is John Heyman. I'm a research staff member here at IDA, and I will be one of your session chairs this morning, all day, along with my colleague Ayushi Verma. We'll be helping Jim and Tom kind of run the course. Mostly I expect reading comments from the Zoom audience to them. So very, very pleased to introduce Jim and Tom, who will be running the DOE short course today. I'm just going to go through a couple things and then try to get out of their way as quickly as possible. So first, I just wanted to go through some administrative remarks before we start the day. They've been flashing here on the PowerPoint slide as you guys have been walking in the room, so you've probably already seen them, but I'll just go through them quickly. If you need to use a restroom, they are around the corner, kind of towards that way. We're in room A, room B is right next to us, and room D is upstairs. You should all have a DataWorks badge. Please wear your badge so that our security staff know who is attending the conference. That's very important for us. If you are an IDA staff and you do have an IDA badge, please don't wear your IDA badge down here in the unclassified area. We have to remove that for photographs, please. Only access designated conference room spaces. A through C are on the first floor down here. D is upstairs by the IDA, same level as the IDA Cafe. If you are a foreign national, everyone please be aware that there are foreign nationals at this at the conference. You will have to, foreign nationals will need to be escorted by staff on and off the elevators if you use the elevator. And for everybody, foreign national or not, please keep all conversations at the unclassified level. So, okay. All right, so that was fairly painless, I hope. I'm very pleased to introduce our two DOE short course instructors, Dr. James Wisnowski and Dr. Tom Donnelly. James Wisnowski, he is a co-founder and principal consultant at EdSurgo. He leads the enterprise consulting and government divisions of EdSurgo. Dr. Wisnowski has consulting experience and expertise in applied statistics, program management, strategic planning, military operations, DOE, reliability engineering, quality engineering, and so on. He has published refereed journal articles and texts in addition to presenting results, new research, and short courses at conferences worldwide. Dr. Tom Donnelly will be leading the afternoon portion of the course. He is systems engineer at JMP Statistical Discovery, supporting users of the JMP software in the defense and aerospace sector. He's been actively using and teaching DOE methods for the past 40 years and to develop and optimize products, processes, and technologies. Tom joined JMP in 2008 after working as an analyst for the modeling, simulation, and analysis branch of the U.S. Army's Edgewood Chemical Biological Center, now DEVCOM CBC. Certainly two experts in statistical theory and practice, and we are very, very pleased to have them this morning. So I will get out of their way and turn it over to Jim to start the course. So thanks, everybody.
Thanks, John. Good morning. I think I'll try this over here, Matt. Is this working if I walk over here? I probably need to turn it on, something like that. Is that good? And it's working with Zoom and everything? Okay. So yeah, Jim Wisnowski, he didn't say Air Force, so I did 20 years in the Air Force as well, taught at the Air Force Academy, and now doing a lot of consulting across a lot of different industries. But the genesis of this course came from last year. Tom and I were at DataWorks, and we were thinking, maybe it'd be good to have a short course where we have a collection of maybe advanced or at least intermediate topics In the past, I know Brad Jones and Doug Montgomery and Drew Landman and a lot of different great folks out there have given talks and short courses. And Tom and I thought maybe there's some specific topics that we could expose some folks to. By what I mean by that would be that, you know, you may not necessarily be using or think you'll need accelerated life tests, but it wouldn't hurt to have an exposure to it so that it could kind of trigger in the future kind of thing. Kind of like reminds me back when in the day when I was a freshman at the Air Force Academy, they had this great planetarium that we'd go and I essentially would sleep, and I got caught sleeping, and you know, the instructor said, "You know how important space is," and went on and on about this, and I'm thinking to myself, space, I'll never care about space. I mean, so turns out, you know, my whole career was founded in space, but so point being is, you know what, maybe some of these topics don't seem initially relevant, but they could potentially be. But more importantly, what we want to do is kind of sharpen the saw, maybe, because all of you likely have very strong DOE backgrounds. And if it was a DOE 101 and we talked fractional factorials up through 2 o'clock, and then we talked some definitive screening designs, you may not get much out of that. So what we're hoping is you all get something from all of the topics that we have. So with that, we do want to be some level of interactivity, and then of course that's hard with this number of folks. In addition to our aggressive schedule, I don't know if you took a look at what we're going to be covering, but each one of those topics could easily be a day. So let me come to the computer here, and if you could put my screen up there, Matt. What you should have got for the materials for the course would have been a whole bunch of PDF files, which are essentially going to be your slides. And if we went through every one of those slides, it would not work well. So it's really a good reference material for you as well. A lot of it is some of the training courses that we teach with JMP kind of a thing. And by the way, this course is in JMP. Many of you are using JMP. But we in no way, shape, or form want to just say that it is all about JMP, because many of these techniques can be done in R, Minitab, and other software. It just happens that, you know, it's convenient for us, and in particular, some of the more advanced methods are more kind of GUI, and you can kind of do a little bit easier. So that's our primary reason. But in any event, you have a lot of good reference material. Some of the slides we'll go over, but many we will not. But most importantly, for those who would like to follow along, and I see some brought computers, that's probably the most effective. You know, how you best learn, of course, would be kind of in a lab where we had a lot of time for you to do exercises. But we're doing the ultra fire hose here, so we're not necessarily going to have time to go through many different practices. But I'll be doing demonstrations. Tom will be doing demonstrations that will be at a pace that you could follow along step by step if you so desire. And that's where you're going to open up the journal. And the journal is kind of probably a good way. Of course, yours will be, you know, if you start disclosing things, you'll kind of see what some of these topics are. And just by kind of a way of introduction, I'm going to go through real quick these topics. And then I'm going to go through them again. So I'm going to just say, hey, here's kind of what we're doing. And then we'll go back and then pick out what maybe the top two topics are that you'd like to cover today, so we get a little bit of an idea as to, okay, a lot of folks are in about mixture experiments kind of a thing. So we can kind of see, you know, where the level of interest is. And John, it's up to you to figure out how to implement that via Zoom. Whether they just want to type it in chat, like, yeah, I'd really like to see accelerated life test, or equivalence testing kind of a thing. So here's how it's going to go. I'll start out with a quick opener. We'll talk log linear variance models, and then Tom is going to talk quite a bit about custom design of experiments, where we talk about some of the constraints and some of the different methodologies whereby you need to fit a design to your problem rather than have your problem fit into an existing design kind of an idea. And then what happens when you have a design and want to do more runs, okay? So that's actually a really important thing is let's do the right runs. That's the augmentation piece. And repairing broken designs. Sometimes our plans don't always go the way they're supposed to, and our tests end up being something other than we hope for. So what do you do then? How can you recover? Split plot, I'm sure a lot of folks are familiar with that, where you have to go, it's as simple as saying, you know, I really don't want to change temperature that much because it really is going to cost me a lot. Or in particular, you could possibly be out on range in the Air Force and realize if you keep changing altitude, you're really going to lose a lot of test time. So you have restrictions on randomization. So quadratic effects and optimality criteria, whether you want what is the difference between alias optimal, I optimal, A optimal, when should you use them? So kind of some tips and some experience there. And then the design comparison here. And then in section 2 is going to be some other useful designs. So mixture experiments, so you can think of it as 100% of something, right? So like if you're talking about, I think our example in here might be Jack Daniel's whiskey, right? So how much corn, how much malt, how much rye do you use? And maybe even a little bit of water kind of thing. So mixture experiments, not necessarily only that. Modern screening designs, you'll see that there's actually quite a few different new capabilities in JUMP. And by the way, I'll be running, and Tom as well, JUMP 18, which you did have a link, I think, that was sent out that you, even if you haven't done it, you can do it now. You can download the trial version for 30 days if you want to follow along. So we're running 18, and there are some updates that we will point out along the way. Measurement systems analysis. So MSA is kind of a big thing. Maybe you've heard of gauge repeatability, reproducibility studies. How good is your instrumentation? Like your measurement system has to be good if you're looking at you're trying to effectively measure response, but if your response is really influenced by poor measurement, then you're really not figuring out what the true contribution of the factors is potentially. So that's MSA. Accelerated life tests. A lot of times we don't have enough time available to precipitate the failures to see what's going on, so we need to accelerate the environment, kind of a thing. So kind of go outside the box, if you will. So accelerated life tests, more in the reliability world is what that's for. And then nonlinear. So not everything in the world is linear, but we do know that we have some great assumptions, and what really fuels DOE is that generally these low-order Taylor series polynomials, we can use response surfaces that well approximate. Well, sometimes that we'd like to get a little bit more, a little bit better precision than that, and we know the nonlinear relationships. Can we take advantage of that in the design? Mod sim. So in section 3, we're going to talk about what about these Latin hypercubes versus some of the hybrid designs. And then we'll talk about adaptive sampling. So a lot of our tests, or a lot of our systems now are autonomous, and they have these boundaries where you have sharp drop-offs in performance. So wouldn't it be nice if we could figure out our new tests are going to be along those boundaries? We don't, where the surface is flat, we don't need to do a lot there. So let's figure out where the boundaries are. Covering arrays are great for like software test or deterministic type systems. So if you want to figure out, like Microsoft Word, if you are always go under Helvetica font size 11 and you're in paragraph mode, then it fails. So how do you figure that out? That's what covering arrays do. And then maybe some of the analysis side. So everything, we do have statistically designed experiments, so a lot of that is the course. But now you have your data, what would you do with it? Well, there's a couple different things. Data transformations. We'll talk about, obviously, in a lot of assumptions go along with our models, and then when we violate some of these assumptions, transformation is our easy way out. Equivalency, so a lot of times what we try to do is prove that these are equal, that the new system is as good as the old system. But the new system, of course, is much less expensive or for whatever reason. We're not really trying to prove that it's better, so it's really an equivalency. So that's a very different question that I think folks don't necessarily pay as much attention to, that is say, oh, I failed to reject the null hypothesis, so 2 thumbs up, good to go. No, that's not exactly right. We really need a better, more rigorous statistical procedures in doing this comparability and equivalence. Functional data, what if your response is not a point, but actually a curve, right? So we do that, you know, if you think of like maybe some radar tracking or something like that. So how do you look at these responses as a curve? And maybe the input factors change the shape of the curve. So a lot of folks do have functional data, but instead of using the whole curve, they'll just take, well, the first peak. What's the value at the first peak, or some average value or something like that. But we're able to take the entire curve and model it. Generalized regression, so so if I'm trying to do some sort of variable selection, there's many different ways to do that. Generalized regression, some of you have heard of lasso, elastic net, those type of methodologies. So we'll kind of dig a little bit deeper into there, and what is the double lasso versus some of these other methodologies in generalized, to include SVEM. Some of you have heard of SVEM, which is self-validated ensemble models, which we can do. And then lastly, we have a Q&A with Brad Jones, who many of you are familiar with. He's kind of the architect of the DOE platform here in JMP. He's since retired from JMP, but he's written obviously many papers recently that are kind of pushing the state of the art in design of experiments. So we have him online at 3 o'clock or so. So save all your hard questions for him. So at a minimum, he'll probably talk a little bit about kind of where the state of the art in research is and some of the challenges that he sees ahead. And obviously, he'd be very interested in understanding, you know, maybe some of the challenges that you have. So anyway, top 2. So I'm going to say it, and then you raise your hand if this is in your top 2. So log linear variance models. Oh, it's going to be, after I show you, you're going to be like, man, if only I knew. That was so cool. So custom DOE foundations. All right. Augmenting a custom DOE. All right. Repairing broken designs. All right. Sounds split plots and restrictions on randomization. All right. Estimating quadratic effects with, I guess that kind of goes with the initial A and D alias optimal design comparison. Mixture experiments. Okay, the front row, all right. I'll be looking at you when we get to mixtures. Modern screening designs. Group orthogonal, supersaturated, yeah, okay. Let's see, what do we got here? Measurement system analysis, MSA, okay. Design of accelerated life tests, ALT, okay. Design for nonlinear analysis, all right, a little bit more. DOE for ModSim with Latin hypercube space filling, super. And then adaptive sampling, all right. Covering arrays, software testers, all right. Data transformations, what is that Box Cox thing? When do I use it? How can I use it? Equivalence testing, I want to prove that they're the same. Functional data, so I got curves instead of points, all right. Generalized, what's the lasso? Okay. And, well, Brad's on one way or another. Who's looking forward to talking to Brad? Excellent. All right, appreciate that. So with that, let me get going with an opener. And the genesis of the opener is I was at a customer facility 2-3 weeks ago and teaching several things, a lot of their manufacturers, so it was a lot of the quality control. But then we got to the DOE piece of it, and they had given me maybe I'll walk over here just to, and They had given me a design that they had done, that they said, hey, if you could kind of talk us through this, this would be helpful. So it turned out it was like 124 runs, and I said, wow, that's a lot of runs. So I said, did we really need to do 124 runs? So I was able to show them that, if we only did 16 runs or so of these 124, I get the exact same answer in terms of what are the active factors and what's the relationships and what are my predicted values. They're all essentially saying the same thing, but you guys took 124 to figure that out, whereas had you done a designed experiment, you could have done it in many fewer. So we'll show you how can you take a subset of runs, and this is potentially useful for you to do the same thing. Like, okay, boss, this is why we kind of need to do design of experiments, because here's what they did last time. And it was I think Tom and I were talking last night. How many did the Saturn V? How many tests did the Saturn V do?
Nearly 500.
Yeah, so 500 tests of a very large system. Could we have learned perhaps as much in fewer than 500 tests? So this is kind of your selling point, right? It's like, okay, this is what they did last time. If you did it my way, this is what we would have learned in 16 runs or 20 runs or 24. Kind of gets their attention, right? So is there a way that we could be more efficient? So let's go ahead and open that up, and I will use it under the context of, I worked with NASA on the Mars rover, the Perseverance. So I've kind of cast it's the same design and responses, but I've kind of changed the variables for their scenario. So we'll go ahead and take a look at that. But ultimately, their justification for why they did 124 instead of 16 was like, well, we really were interested more in the robustness and the variance, right? So a lot of times what we do is mean models. What are the drivers that are influencing my response? Well, don't forget, there's the other side of the house. How stable is that? There may be areas of the design space, the operational envelope, where you have very large scatter, right? That you don't have consistency in your response. So they said, well, that's what we were trying to take care of. That's where we're going to use the log linear variance models. So off we go. So I'm going to do the opener here. And what I've got is 4 factors: rate, angle, hardness, and percussion. So this is drilling. So what they're doing on Mars is they are drilling. They are putting these cores into test tubes. And at some point, they're going to go back and get them. They're just putting them in the tubes now. And there's overall a quality measure as to how good is my core. And it's a function of what is the drilling rate and what's the angle that your drill is at, what's the hardness of the rock, and the percussion is kind of like your hammering, if you can think of, like when you do drilling, sometimes you get frustrated and you start pounding. There's actually utility in that. That's called percussion. So I'm just going to go ahead and create a model for quality here with my 124 rows. So I'll go ahead and just do my analyze, and this will kind of get us warmed up, right? So we're just going to do a fit model, and I'm going to take my 4 inputs, and I'll do a macro, and I'm going to do a response surface design. So now I've got my response surface in there, but what's nice about this display here, by the way, in Jump 18, you can also put in the header graphs here. You now have your header statistics, which could be helpful. Point being, though, percussion we don't want to square, right? Because you really wouldn't do well squaring something that's only at 2 levels. So I'm going to take the percussion, square it out right here. I'm going to remove it. And I am trying to predict, under primary responses, I do want to predict the quality. So I'll just do the standard least squares, and I should be all right. Right? This isn't usually the case. I'm not such data-rich environment, so I don't have to worry about my degrees of freedom per se. So I'll just go ahead and make my reduced model here until everything is, what is that, 0.04? So I guess that's my model. So I'll go ahead and save this response. So under Save Columns, I'm going to save that prediction formula. So what we know is the prediction profiler here is an awfully useful display to communicate what's going on with the system, right? So we can see that quality really has quadratic effects in angle and hardness, and kind of just the opposite, right? That one is smiling and one is frowning, kind of a thing. And that both rate and percussion have a negative slope. So that's what we learned. Now, here is what we'll do, is we will say, what if I could save you 100 runs? Which 100 of these would you do? So that's where the DOE Custom Designer comes into play. It allows you to select. So I'll come under DOE, and I will come under Custom Design, and right here where we have this Select Covariate Factors. So I'll go ahead and put in these 4 input factors. So now I've got my rate, angle, hardness, and percussion. And I do want to, in this case, you don't have to put in, you don't read in the response that's already there. You're just trying to create the design from this. Next up, I'll just hit continue. And what I want is a response surface model, but I'm going to take out that percussion squared. And then this is where it all happens, the magic. How many runs do you want? What subset do you want? Well, I want to save them 100 runs. So back in the day, there was a show called Name That Tune. It's like, I can name that tune in 24 runs. So in this particular case, you could have some highlighted or selected rows right here, and you could force those runs in. So this is kind of like, well, you know, what if we knew we had to do those original 8 runs, so I could force those original 8 runs in, and then rather than doing the next, you know, subset of, 20, maybe I could do something fewer than that. So you could select what you want. But right now, we're just going to let JMP tell us what it is that we want. And then you'll note here is an optimality criterion. We'll go with the recommended, but you can choose which one you want, and Tom is going to talk a lot about the differences between these guys and when you might want to use one over another. So it's about 10 seconds or so, I should have a new design of 24 runs. So what I'll do is I can go ahead and make this table, and this is my subsetted design, and we can kind of see that it too is pretty balanced, right? But that's interesting that we could run that design, but let's see what would have happened if those were the only 24 runs that we did. What would we have learned? So to do that, JMP has selected the 24 runs of interest. So I can go ahead and rerun my fit model only using those 24 runs. So what I can do is I'll just do rows, and I will invert the selection. So row selection, invert row selection. And then I'll just hide and exclude those guys. So now I'm only using 24 runs. So I'll do the same thing. I'll do analyze, fit model, and I'll recall. Okay, so I can recall, and I'm getting the same model, and hopefully I don't have the percussion squared in there. So this is, you do need to know, do you have enough degrees of freedom to do this? Because you got 4 mains and what, 6 two-factor interactions and 4 quadratics. So yeah, I'll be all right. So I'll go ahead and run this guy and do my reduction here. Oop. One at a time. Probably should have done them all at once. Okay, so now I've got my model, and look at that. Does that profiler look like kind of like what we just saw? Sure does. We got the frown in the angle and then the smile in the hardness. But I can look at those side by side. I'll go ahead and save this column again. I'll save that prediction formula. And then now what I have is these two prediction formulas on the end, and I can compare them. So I'll just come under graph, and there's a profiler, and I'll just put in those two prediction formulas, and then now I've got them side by side. And boy, awfully similar results. So what did you learn in the 100 runs? They're like, well, we had to test to see if the standard deviations were the same. We really wanted to see if there's variance. So we said, okay, if that's your goal, then we also could do something else that would still conserve some of the runs. So when you're trying to estimate variance effects, so this is a mean model, right? You're trying to figure out what the mean quality is here. But if we're trying to estimate what the variability of the quality is across the design space, it's going to take more runs, okay? But not as many as 100 more runs. So can we kind of maybe get away with something less than that? So I'm going to return to the journal for a moment. And here is a single factor test. So if I open up the single factor test, what I want to see is I have a variant here and then I have a performance. The variant is either a Commander, a Hoya Saxa, or a Wizard, or a Capital. Does sound like familiar names around this region? So I grew up in the Oriole land, and I paid a lot of money to the Hoya Saxaville for my son, so I'm tied. So here's what you might do, is you might want to say, is there a difference between these guys? So let me just show real quick what the plot looks like of this, just so we get a little bit of a sense for what's going on, right? So if I look at these guys, I kind of think Wizard has a lot more variability, right? Versus maybe Commander is pretty tight, and Oriole as well. But there's a lot more variability in the Wizard. So keep that in mind. So I'm going to come under Analyze, Fit Model, and it's I changed this. It was a biopharma example with buffer in there for your variant, but we're still okay. So we're just going to add variant. So performance and variant with under standard least squares we run, and then we see down here we get a profiler. Okay. And here's my problem with the profiler, is I get it that maybe the mean for Wizard is higher, okay, and the mean for Oriole and Hoya Saxa are maybe the same. That's all interesting, but you just showed me a plot where the variability with Wizard is, you know, twice or three times maybe the Commander and Oriole. So why would I expect to see confidence limits, which is what the end of the blue bands are, why would they be the same? Why would they be constant across all 5 treatments? It's like, that's a good point. So what I should do is maybe take into account the individual variability. So I'll go ahead and set this guy aside for now and do this again with the log linear variance that none of you like. So let's see what that does for us. So we'll do Analyze, Fit Model. Yeah. Next time I'll fix that. So I put my variant under there. Instead of standard least squares, there's that guy just resting on the bottom, the log linear variance. So my main effects will be the variant. This, of course, you could do with very complex models. And then my variance effects is also going to be variant. They don't have to be the same. So if we had 4 factors, like they did in the initial one I was showing you, you could do your 4-factor mean model, but really it's only the percussion that I think is where I have my variance issues. So then you model that as separate, just one main effect for that. So anyway, we can go ahead and run this guy. And now what we'll note is we initially saw that there was no statistical difference amongst all these guys. Now we see that maybe in the mean that the commander mean is perhaps a little bit different. But more importantly, I have my variance parameter estimates, and I note that the variance of Wizard at 2.4 is significantly different from the rest of them. Similarly, variance of Commander is significantly different from the rest as well. And we know that that's because one is very small and then the Wizard is very high. But here's the visual that would maybe make this all fit together. So when I'm looking now at my profiler, it's this right here that I'm looking at. So does it make sense that my confidence interval for Wizard is much higher? See, the means are the same as the original profiler, right? But now my confidence intervals are perhaps a little bit more in line with expectations based on the transmission of that standard error issue. Are you a believer now? Like, maybe there is something to that. What did it cost me? It didn't cost me extra runs. It's just a different and analytical method. And that's maybe a little bit of a theme for the day, is a lot of the things that we'll show you are just ideas for you to tee up and see if it helps. Maybe it teases out some extra information that could be a potential help in a decision process. But now at least you have these confidence intervals much, more adequately represented. And there is another example in there with injection molding. And then I can go back to my original guy here. And what I'll do is I'll put on a data filter on my rep. So there's like 9 reps or so in here. So what I'm going to do is I'm going to use my primary rep. Let's see. Yeah. I'll use my primary rep in my first, or I guess second rep here. And then I'll show and include. So now I've got 30. So I've got 30 observations of which I know that there are replicates in here. So when you do, and I won't do it in the interest of time, but center points work. When you replicate center points, you can do a log linear variance model. You do need something replicated, kind of a thing. So in my analysis now, I'll come under Analyze, and I'll do the fit model. And in this particular case, I'm going to do my personality is going to be the log linear variance, and my main effects, I can still do my response surface here. And then my variance effects, it's only going to be for percussion. So I add in percussion. So now I can go ahead and run. Jump, I tell you, it requires a response. Come on, man. All right, so we do want to do quality as our response. Getting ahead of myself. So anyway, there's all your parameter estimates, which you can figure out which ones are statistically significant, and then go back and create your new mean model. But importantly, I see down here that I do have a statistically significant percussion effect. Again, what does that mean? It means when I look at the profiler down here, well, why did that not work? Got biased estimates here. Oh, remember I said that I knew it was going to get me. The percussion, right, is squared. You can't square the percussion. So all of that, I think, is what got us. So if I fit model and I recall, let's try this, but take out that percussion squared and run it and see if the profiler makes any more sense now. If not, there we go. So here's the game, right, is that in general, as the percussion increases, so too does the variance. And look what happens to the confidence intervals. Hard for you guys to see this colored in on the screen, but you see the blue in the mean model right here? Do you see where they are? And then watch as my percussion decreases. Do you see how tighter those bands get? In this case, it's not, wildly different, but it could be, right? If you look at the hardness in particular, so you're seeing that your confidence interval here is going to increase when you're at the higher end of percussion. Log linear variance models we have had a lot of success with across a lot of different industries. That again, it doesn't necessarily cost you per se. In many cases, it's just a different way to do the analysis. And I know there's other ways. Tom will talk about some transformation, as well as you could just model the standard deviation, right? So I could, what they did was they did a tabulate and figured out what's the standard deviation for each of those replicates, and then modeled where is it the greatest. And guess what? They found out that it was really this fourth variable, percussion, that was the big driver. So with that, that's kind of a little bit of an intro, kind of get the feet wet, and thinking about modeling, and maybe something you hadn't thought about is using a log linear variance model. I think even if you look in the help documentation, it says, we believe these should be used more often. So with that, questions? Right on. Tom, you're up.
Okay. I'm checking with John here what the break schedule is, just in case people are going, because I think if I get going, I can keep going. So 40 years I've been doing design of experiments. I'd never done a log linear. Just learned something from Jim. Oh, I'm up here.
Success. One person learned something today.
And I have to say, the voting, I was like, uh-oh, we're talking to the wrong audience. I was expecting more hands. At least one of the areas where the hands went up. Get myself set here. I got to plug in. Trying to do two things at once. Okay. Where was I? I was talking about log linear and the voting. So in the voting, the things I saw lots of hands go up on was like fixing broken designs. That one looked like a lot of hands went up. There's actually a lot of build to that. So we're going to get there. You also saw something that also I had an example of, but Jim's done it here, is you can take data and use it as a candidate set to find, hey, is there a design experiment within this sort of historical haphazardly collected data? And so I may have another example of that that's in Jim's case, it looked more like a designed experiment they did a lot of replications of, as opposed to, hey, we got 124 things, we've just been doing a bunch of tests. And you're kind of all over the place. So with that, I'll try to get going here. We got lots of topics. I'm not even going to read them all here. But the whole point, and Jim kind of started off with this, is the main road we're following here is that we want to create experimental designs for real-world problems. Okay? Too often, historically, what people have done is, you take a short course on design of experiments, you learn about fractional factorials, you go out to the lab. Well, I got 8 levels for this factor. That's not in the course. And so, well, then maybe what we'll do is think real hard about the 8 and go, well, if we take this one and this one, they're the most different, everybody else falls in between. So the idea was, we're going to try to force our design, our problem into that design. Well, the key to making the designs for real-world problems is to use some type of a model-driven, computer-generated design. And we've been able to do this now actually since the 80s. Okay, so when they say I've been doing this about 40 years, I actually was a partner in the first DOE software company that was founded in 1981 as a statistician at DuPont who was doing algorithmic design back then. And it was all about how do we solve real-world problems. So that's the main road, and then these are all sort of side roads. Constraints, augmenting designs, repair and broken, hard to change. Again, you can read the whole list there. Then there are some other areas. Again, we didn't get a lot of votes on some of these, but screening designs, to me, screening designs almost always work. You can almost always be successful, and from my perspective, too often what people do is they think real hard about a big problem, and they say these are probably the 3 or 4 factors that are really where the solution is. And yet they had a whole bunch, that they could have picked from. Well, it's actually better to do designs with lots of factors where you don't end up necessarily with a model that predicts, but it makes it very clear these are the dominant few, and these things really don't do anything. Okay, so screening is very important. And there are lots of new screening designs that have come out. So I've, again, listed many of them there. Happy to show you some of those and their relative performance to sort of classic screening designs. Let me just say, classic screening designs are great designs. They have solved all sorts of problems, okay? Why would we not want to use them? Well, we can do a little better today with some other designs, and some of these are for broader problems, okay? And then the computer simulation, this is an area we actually got a lot of hands went up. Okay, so we are going to do a session on efficient modeling and simulation and talk about these various design types. And then these sort of third group of topics was kind of under more the catch-all that Jim was talking about with analytics. So things like data transformations, you sort of saw that in his log linear example. Okay, it turns out for me, transformations make a huge difference. And I'm not a statistician. Matter of fact, I've never taken a formal statistics course in my life. I'm just a design of experiments kind of geek who said, this is a great solution. I'm going to keep using this thing. Well, the guy who founded that first DOE software company used to say to me, Tom, you love these transformations, but at the end of the day, you didn't take any more data, okay? The top of the hill is still near the highest data point. The bottom of the valley is where the lowest data point is. It just is a better way of representing, and you get answers that make physical sense. One of the most embarrassing things you can do as a design of experiment or first, young gun with it, you go out and you make predictions where your yield is in excess of 100%. How did that happen? I'm predicting negative resistivities. How can that happen? I'm getting negative defects per unit area. And you start showing these results to people and they go, I don't think you really know what you're doing. And that's where transformations can help you, not have those kinds of problems. So we're going to go there. Checkpoints, I don't even know that we really have a formal set of slides on this. But again, not being a statistician, for me, design of experiments is all about, I analyze it, I make predictions, I've got these limits, and I go run tests. I go run checkpoints. If they fall within the limits, I trust this model. If they don't fall within the limits, I don't care what those p-values are, the r-squares. That doesn't do it for me as a non-statistician. So I think checkpoints are very, very, very important. Okay? Nonlinear designs, we'll talk about binary testing and these other topics that Jim has already listed, accelerated life test, measurement system analysis. Functional data has really come on. Okay, so this is where the response is a curve. It can even be spectra. And so I think if we get to that example, one of the examples, I actually have 2 different examples of it where people have done historically mixture experiments where they've looked at blending, say, 3 different ingredients together and then do things like Raman spectroscopy or NMR spectroscopy. I mean, we're talking lots and lots and lots of little peaks. And it turns out they've done hundreds of these because they had no way to really do this but sort of interpolate between them. We can now, with a very, very tiny subset of those from a designed experiment, we can now predict that very, very complex spectral shape for blends we've never done. And better yet, we can take those spectral, if you gave me a spectral shape and you said, this is from blending these things together, I can take that spectra and tell you what the blend was that you actually put together. So this area has really come on with design of experiments, so for functional data. Okay, so those are topics. Again, how many people here have taken a DOE course before? How many of you have never taken a DOE course before? Wow, okay, that's a fair number of you. So normally I don't have to sell DOE to you, but I think the reasons we want to do this, quicker answers, lower costs, solve bigger problems. You'll see my list here. You've seen Jim already using this profiler, being able to say, what happens if I take this, pressure up or down? What does that do to the prediction? What does it do to the confidence intervals? So we've talked a little bit about screening. That's identifying important factors. There's sensitivity and trade space analysis. And when I went to working for the Army, which is now about 20 years ago, I walked in the door having worked sort of in industry where everybody is, how can I make it faster, cheaper, more robust? We want to find the optimum set of conditions so we can make money. And then I started working for the Army. And quite frankly, they didn't care about making money. But they cared about things like, does this work within this operational envelope that we've specified? There are requirements. Well, to answer that question about do we fit into the requirements is the same type of modeling. It's going to be some type of response surface to get that characterization. So characterizing an operating region and optimization both require the same type of designs. And the other thing I ran into is, how could we be more efficient? And you can do this by running subsets of all possible combinations. Okay, so for the same resources and constraints, we can solve bigger problems. And then if we can do this sequentially, we can be as cost effective as possible and run no more trials than are needed to get a useful answer. So I have a couple of stories to remind myself at the bottom here. One says Agent Fate 10,000 plus. I come into the Army in 2005, and they're running, and they're way behind testing of a particular, they were looking at different chemical agents on different substrates in wind tunnels that fit inside fume hoods. So these are tiny wind tunnels, but they're looking at evaporation rates. And they're literally brute forcing this problem. They have like 10,000 plus experiments they need to run. And they're just way behind. So I looked at it from a design of experiments point of view and showed them, again, with just around 100 experiments, you're going to get like the 90% answer. And so, they ran these designs, and all of a sudden they're back on track. But, the point is, if you're brute forcing it, you're probably already running into, the limitations of just trying all combinations. So how many people have ever done that? I'm just going to run every combination. Okay, I'm glad you admitted it. More people have done it than just you, I can tell you. So the other thing I ran into was an Air Force simulation study, and we're going to see this one when we do efficient modeling and simulation. They were looking at a simulation of a biological attack of Kunsan Air Base, and they had 6 different agents, there were a bunch of other factors. The point is, all told, there were 648 combinations. It was a completely deterministic simulation. We do it and analyze it, and what I was able to show them was, with just 36 of those 648, I could get them the 95% answer. And with 108 of the 640, I can get them the 99.9% answer. And they went, if we knew you could do this, we wouldn't have just looked at 6 factors, we would have looked at 15. Okay, so again, this is the why do we use DOE. We can solve much bigger problems, faster, cheaper. So this is very often the example, if I have to do like one slide for a group, why would I want to use DOE? And this data set is actually from a real experiment. I think I published something in American Laboratory in 1989 with these data. And so you'll see words like sensitizer 1, sensitizer 2, dye reaction time, speed, contrast. These data are from a photographic emulsion. I mean, nowadays everybody has a digital camera. But back then, you loaded film. And so they were looking for what combinations of settings could give them what they had some goals of maximizing the speed, maximizing the contrast, minimizing the cost. And so this is the 27-run experiment that they went off and did. Now, in the upper right, I've got that same prediction profiler that Jim's been showing, but I've dressed it up. The colored regions are where we do not meet requirements, okay? And I put some little numbers there that show you we are supposed to be above 5.3 for speed, above 0.7 for contrast, 0.28 for cost. And down below is something called desirability. Desirability is on a scale of 0 to 1. 0 is what we don't want, 1 is what we do want. So over here on the right, you can see we want a lower cost, but we want to increase contrast and increase speed. So if I were to move my settings to the top of the desirability hill, I would come up with a set of conditions that should be a good trade-off. So let me sort of get this going here. Okay, there it is. It's starting to move. So now this is me changing sensitizer, and there's two things happening. The predictions are changing, and the slopes of the relationships in some of the other columns are changing. Those are indicative of an interaction. Well, I'm moving up that desirability hill, and all of my answers are now in the white region, so I'm meeting all my requirements. But why am I doing that manually? I can just ask the computer, why don't you find the top of the hill? And there's the best trade-off. Now, this is where I'm going to pause it for a second here. I thought I was going to pause it for a second there. This is where, when you have results and you brief decision makers, this is where your job as the technologist is to show them this is our understanding of the process. They may come in here and say, hey, can you take some more cost out if you give up a little bit on contrast? That's a business decision, okay? That's the kind of information you want to deliver. So down below here, walk away for a second, I've actually saved different sets of conditions. The first one is everything's equally important. Well, sometimes the person in the room, particularly the biggest decision maker, may say, I think cost should be much lower. So they may increase the weight or the importance on that optimization to, in this case, 6 times as much. So if I get this going again, and I'll just move it along here. So right about here. You can see we're looking at the sort of this best trade-off under an increased weighting scheme. Now that I dropped the cost 20%, but I'm no longer meeting requirements on speed. So I go back in, change the weight on those, and now I've got an answer, maybe not quite as low as before, but now I am meeting all requirements. And sometimes the answer here is, you can't do it. Kill this product, kill this program. You need to go find some, if this is the best you can do with this combinations of factors, sometimes that answer is, it's not good enough, okay? This is where you want to get to with designed experiments as quickly as possible, where you have this kind of decision making that you can present to your leaders. Okay, you know, I haven't worked only in the DoD, and so I once taught a course at a pizza summit held by one of the major pizza companies, and this is how they made sure that all the oven vendors delivered them ovens that did what they want. They had 8x10 glossies of what they want the crust, the cheese, color to look like in a big binder, and they give it to each of, this is the 80s. You give them this binder and you say, when we say cheese color is 4.5, it looks like between the picture 4 and the picture 5. Okay? This is still stuff that we do today. Sometimes what we have is you know, an image that we need to try to match. But the goal here is, how do you do this? And I've got some overlapping regions again. So the white region is, again, where things are acceptable. And if I overlay all these contour plots, you can see there's a sort of a white region where everything is acceptable. So again, it's this idea of getting that best trade-off. And I can also, with that same desirability, only difference here is I've got targets for everything instead of max or min. And so there's my best trade-off. You can also do this with mixture formulation. So at the top here, what we've got are hardness values. Okay, so this is something that, you know, is on this table. It goes all the way from chewing gum to hard hat. Well, you might have customers that come to you and say, I want a specific hardness for this product. And of course, they would also like that at the lowest cost. So what you can do is, again, look at a formulation where in this case I've got 5 different ingredients. So binder, plasticizer, A monomer. Mike, go away. I guess I should shut my teams off. He's a persistent guy. Okay, so I've got my 5 components there, and once again I can say, find me that best hardness, my target hardness at the lowest cost. And you can even do this, you'll notice these vertical lines are solid red as opposed to dotted red lines. And what that indicates is I have fixed the B monomer and the co-binder. In other words, do the optimization, but do it without varying these two. Okay? So very easy to optimize there. Okay. So, getting back to, this is sort of the why do we do DOE. Now, most of you have probably seen a definition like this. Again, it sounds like there's a handful of people, more than a handful of people. This is their first DOE class. But we usually think of a design of experiments as the purposeful control of the inputs. We usually call them factors. Some people call them variables. In such a way as to deduce their relationships, if any, with the output. We often call them responses. So this, I have a data set that we may bring up later called tablet production. And this is the sort of flow chart for it. These are pharmaceutical tablets. And we're looking at things like everywhere there's an arrow going into a green box, think of that as like a knob on the equipment, okay? That's something we can change and vary. And eventually, we output a dissolution rate and a coating uniformity. So that's the response of interest here. So that's how if you were to open up almost any design of experiments textbook, that's what they would tell you. This is the alternative definition that I like. This really is, I learned this from my mentor, the founder of that first DOE software company. He always talked about your collection of trials that you will run to support a proposed model. So if my model is simple, just main effects in 2 factors, that's a plane, I don't need that many trials. So this image in the upper right here, this, for those of you that have taken a classic course, that would be a half fraction factorial in 3 factors. So the average of the 2 on the left versus the average of the 2 on the right, that difference is the contrast for the effect in that x1 direction. Okay? Now, that's great, and that works well as we go up in dimensions. So if we have 10 factors, we only need about 11 trials to actually fit the model. Okay? So you don't need very many. But if you wanted to support the model in the middle of the screen, so right here, we call this an interaction model. And so an interaction is, if I'm looking at the behavior of y versus x2, notice on this edge, that has a positive slope. But if I go to this edge and I say, do an experiment, y versus x2 at high x1, I get a negative slope. Okay, where does this happen? I see Scott Hunter sitting over here. I've known Scott. He worked out at Dugway Proving Ground when I was working at Edgewood Chemical Biological Center, so the sort of the West Test Center and the East Test Center. What if we both did an experiment versus x2, but we didn't communicate where x1 is? Scott's getting positive behavior and I'm getting negative behavior. Who's right? Well, we're actually sort of both right, but we're both wrong because we're not communicating where that interacting variable is. Okay? So if we wanted to get that, we both need to test with both variables, x1 and x2, and then you get a shape where the edges can have a different slope. So that's an interaction. You can't fit this model to this design. There's not enough data. Okay? Now, that works great, but if there's really curvature in the process, okay, you need what's called a response surface design. You've heard us say that several times. Notice how the yellow points here are all in the middle of faces. So that gives us mid-levels. If all you have are corners, all your model can do is look like a twisted plane. And if you said, where's the max or where's the min, it's got to be a corner of the space. You can't have an answer anywhere inside the cube if you don't have curvature in the model, which is why we like to go to response surface designs if we can. So again, here's the classic definition: purposeful control, okay? So we can, determine any relationships. But I think the other way, which I really like, is pick your model and then pick a design that will support it, okay? And this opens the door to supporting models where some of the factors have 8 levels. Some of the factors have constraints. Do you have a question?
So does that mean that from this point of view, when you pick, at some point you ask, what's the most complicated model that I want to test for? Because you're sort of, for instance, saying, what's the highest level interaction that I want to be able to test for? Because if it's there, then we would leave open the possibility that even more complex model would do even better. Did that make sense?
I think so, but again, not just my 40 years of doing this,
Yeah.
but if you read most textbooks, there are main effects, there are 2-factor interactions, there may be 3-factor interactions, there may be even higher. If you saw the Drew Landman course, he talked about some of the wind tunnel testing for some EVTOL, where they looked at even 5th-order models. That happens rarely. We don't normally go into a fresh design thinking the world is super complex like that. I mean, for years I had never seen a 3-factor interaction until finally a statistician at Kraft, Jacob Suchard, said the difference between a good chocolate and a great chocolate is a 3-way interaction, and knowing where it is. Okay, so they do exist, but most industrial processes, and again, think over narrow factor ranges, we can approximate with low-order polynomials.
Okay.
Now, when we get into the, I realize I walked away from the microphone. When we get into the computer experiments in particular, you can start to have models that are more complex, things where things fall off a cliff or there's a spike in there, and we're going to need more levels to the design. Okay, but for most sort of real-world experimentation, the assumption of low-order polynomial has proven to be very effective. Jim also will probably talk more to it, but there's this method called SVEM, self-validating ensemble modeling, that's proving itself to be fairly effective in complex mixture experimentation. I think he's done it with some hypersonic vehicle fuel, but we've also seen it in the pharmaceutical industry. So there can be more complex models than what I'm showing here, but these assumptions and these low-order polynomials have worked very, very well for a long time.
Okay, thank you.
Tom, we'll
Yeah.
take a break at 10:15,
Okay.
just so you know.
Yeah, I'll find a good spot to break there. So again, these are kind of the words of what we just had. It's still this idea of proposing a model and building a collection of trials to support it. There's basically 2 models. There's a first-order model, X1, X2, X3 to however many factors, and we call that screening. The goals here are often ranking factor importance, often finding a winner, but rarely are we walking into the door saying, I can predict everything with just a main effects model. That's just not, in most processes, going to happen. You use this when you have many factors, and I have a 6 with a question mark there. It kind of depends on how costly your experimentation is. Sometimes lots of factors is easy. I have an example from Edgewood Chemical Biological Center within the last month. I was talking to someone there doing experimentation where they are now blending in a mixture experiment 40 different ingredients, and they have a computer-controlled blending system that can run 1,500 experiments in 2 days. They are now optimizing 40 component processes in 2 days, and it used to take them months to get there with maybe 8 components. So my point here is that complexity can go up, if you have the technology to keep up with it, okay? But again, the models are either first order, and again, that typically means maybe 6 or more factors in your characterization. But if you go to the second order model, so now we're adding those interaction terms, those are the cross products, And then the squared terms, if your factors are continuous, we often call the continuous designs response surface designs, but in general, just think of them as the difference between ranking and predicting. That's kind of the difference between first order and second order. And so again, the goals here include developing a predictive model and characterizing that operating region. Rarely do I see people doing this with much more than 6 factors. Just gave you an example where they're doing it with 40 because they have the technology. But most response surface designs are going to be on the order of 6 or fewer.
Can you just maybe give an example of what you mean by characterizing the operating region? You mean like explicitly saying what space is available?
Well, it's more like we want to make sure we cover a region, and we want to know the performance in that region. So, I don't know, there's got to be an Air Force person here. I see a guy in a suit here calling on you. You know, when you're told you get into this plane, it says, you know what, this is the operating window for it. You don't ever want to exceed, you know, a certain velocity at a certain turn angle. I don't know, maybe because you black out. I mean, so we want to know the performance, but we want to know where that operating region is. Does that make sense?
Yeah.
I don't know if that was a good enough analogy. Okay, so those are our definitions. This is how I would often give my classic response surface DOE summary. So you can see I've got these 3 blocks. On the upper left one, I've got the red corners and one in the center. The middle block, it's like the opposite 4, or the complementary 4 corners. They each make a tetrahedron in the center. And on the far right, I've got the center of all the faces. Every one of those can fit the model on the lower left, the plane. Okay, it's a very simple model. There's enough data in any one of those blocks. But if I've got my checkpoints where the red and the orange stars are, I might not do a very good job of predicting, because at that point, I'm just screening. Now, in the middle window, I've got that twisted plane. So this is me supporting the interactions in the process. And now maybe I'm doing a good job where the orange star is, but I'm still not predicting that red star very well, because that surface can't curve up. The only way it can curve up is if I have data at the midpoints of the factors, and that's what we have on the right. And now you'll notice here, remember I said, okay, so first of all, main effects model, these edges are parallel. Interaction model, they can now be different. Okay, when I add the curvature, notice that this edge is still predominantly positive slope, but it's got a concave down behavior as well. This edge is still predominantly negative slope, but it's got a concave down behavior. But that concave behavior is what's led us fitting that red star here for this checkpoint. Okay, so this is just sort of increasing model complexity that we can support, and then fitting those models to it, and we see that we get better and better predictive capability. Okay, so these are what those polynomial models look like. Okay, and let me just, this slide has a lot of fine print on it, but the point here is to get you to sort of look at how is the world exploding. We can only draw the picture to 2 and 3 dimensions here. So if you think of the left case with first order models, with 3 factors, there's only 8 corners. This room is a great 3-factor design space. If I go to 6 factors, there's 64 corners. 10 factors, there's 1,000 corners. 20 factors, there's 1,000,000 corners. So when you start doing screening designs with 10 to 20 factors, and your design only has to be 20 runs, you are running a very, 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 very tiny subset of all the corners in that space. So yes, you'll get a ranking of the factors, but don't expect yourself to be predicting. But that's the goal of the screening, is to shrink that large list down. The next model, the next step to second order in the middle, just adds the interaction terms. Now with 2 factors, there's just one interaction, x1 and x2. With 3 factors, it turns out there are 3 interactions. With 10 factors, there's 45 interactions. And with 20 factors, I can't do the math in my head completely, but there's like almost 200 interactions, okay? So this is the part of the model that's exploding in size. We get to adding the curvature part, and this just goes up as the number of factors. So if you have K factors and you got 3 factors, it's only 3 bigger than your interaction model. At 10 factors, it's only 10 bigger than your interaction model, okay? So what's the purpose of this slide? Too often when people take a traditional course, I feel they talk about do the screening, maybe with some type of fractional factorial, and then maybe augment it to support more interactions, and then add the curvature. I would say it's not that much work to just go all the way to add the curvature. And particularly with models, and we'll see augmentation, we'll be able to take a screening design and move it all the way to response surface, and it's not that much more work than if you had done it in, it's not that much more work than if you just only went to the second order stage. And my point of that is, if you're after prediction, if you're after optimization, a 2-level design, your answer is always a corner. So don't let yourself be forced into that corner. Okay, so we're at this slide where we're talking about a 6-step DOE process: describe, specify, design, collect, fit, predict. Pretty much after the first 2 steps, the rest just kind of happens almost automatically. You've made the real decisions in the describe and specify part. And my comment here is design of experiments cannot be blindly slapped on a process ignorant of the science and engineering behind it. You will fail, okay? And this is where I say, you know, when we identify the goals, the responses, the factors, that's what the I hope unreadable blue boxes are. Those are the kinds of questions. I used to send these out to people when I worked for the Army, and they would say, can you help us with this? I would send over a list of questions, because too often I showed up and they said, we thought it all down to these 3 factors. And I almost always said, so you're really not concerned about, and I would start to list factors, and they said, well, yeah, okay. So I try to back them up to do some screening. Okay, so those, setting the goals, the responses, the factors, that's really scientific expertise. And you can't skip that part. And then when it's the specified part, I really do think this is pretty easy. It's either a first order model or a second order model. So this slide, I can't tell you exactly if it's 35 years old or older, but this is when I first learned about experimentation. And this is the subject matter expertise, timid versus bold range setting, okay? If you don't turn the knob very much, it can't have a big effect, okay? And the bigger the effect you make, the noise stays the same. So the picture on the left is sort of really bad luck. I only did 2 experiments. I hardly turned the knob at all. And if I take the data I have and fit a line, I get the blue line on the left, and I got the completely incorrect, guess at the behavior, the true behavior between Y and X. Where if I'm more bold in the middle, you can see even with the bad luck of just 2 observations, one at each of the opposite tails of the distribution of variability, I at least get the right slope. Now, if you take enough data, the ones on the right, so I've got lots and lots of data, even if I'm, timid, I might still get the right answer. But the whole idea is we want to do fewer tests. So you want meaningful ranges, okay, to test over. Now, this is where, again, I'll throw out, I don't know very much about curing epoxy, let's say, and I look at the sheet and it says, oh, test between, you should cure this at 150 C for 30 minutes. Well, I'll do a test between 149.9 and 150.1 and 29 and 31 minutes. You're probably snickering because, really, can you even measure your temperature that accurately? At the same time, I'm going to go 0 to 1,000 Kelvin. Complete ignorance of what happens in the chemistry of curing epoxy. So absolutely, you want to be as bold as possible without breaking the process. Okay, this is probably the most important slide in this deck right here. And it's all about reasons why classical designs likely will not work. This is all about how do we make our designs fit the problem, not make the problems fit the designs. So there are lots of different types of control variables or factors. There's continuous and quantitative, categorical or qualitative, mixture or formulation, there's blocking, there's probably even a few others if you look at the list in JMP, but those are the dominant ones, okay? And sometimes you have to work with combinations of all of these. And sometimes certain combinations of these don't work. They're too costly, they're unsafe, they break the process. You can have hard to change factors. Jim's already talked about it. Temperature is usually the candidate for this. You know, if you have a huge oven and you can't take that temperature up and down willy-nilly, it takes a day for it to stabilize every time you change it. So what do? You do all the low temperature one day, all the high temperature the other day. But you've opened the door to correlation with what if the first day was, you know, dry and sunny and the next day was cold and rainy? You know, well, was it the weather change or was it the temperature change of the oven? And then sometimes we break our designs, we've been too bold. You can take existing trials and add on to them subject to constraints to repair that broken design. And we're going to show examples of all of these. But these are the kind of real world issues that, you know, if you have your textbook design, you look at it and you go, well, this doesn't fit. I need to make changes. And you start making changes to your process and as opposed to the design. So here are examples of categorical factors and responses. So again, I worked at the Army at Edgewood. We might be looking at 3 different agents with 4 different decontaminants on 8 different materials. So I got a little coupon of each of those materials. Why those 8 materials? If you think about it, that's what you make a plane out of. That's what you make it. Almost anything, you make electronics out of it. So if it ever got chemical agent on it, somebody wants to know the answer to what happened when you put that decontaminant on that material. This is where I go to my textbook, and I might have 2x2x2s or 3x3x3s, and all of a sudden I'm going, can't fit all the materials in. Maybe I'll use steel and silicone because they're the extremes. That's not really answering the mail. Continuous factors, think of these as things where you can adjust it, you know, very minutely, you know, to some really tiny level. I'm going to try to pick up the speed a little bit. Discrete numeric, I'll have some more examples of these, but basically you have to have integer numbers of teeth on your sprockets. If you've got, you know, something halfway between 2 levels and it's not an integer, your bike's not going to work. So your factors are only available at certain discrete levels. That's why it's called discrete numeric. So it actually designs like categorical, but it models like continuous. Okay, I do a lot of examples with pizza, you'll see. And again, the pie pans, you could order a pie pan at, say, 12.5 inches, but that's not a stock one. You can buy a 12, you can buy a 14, but, you know, so you're stuck with using those particular sizes. So again, there's basically at this point, you know, I've talked about these 3 different types of factors. Again, here's a whole bunch of continuous, and I purposely went and found analog examples. I could find a valve somewhere and turn it till I get the pressure right to that number, okay? But in theory, I could get any number for it. I'm buying bolts. Does it matter if I buy them from Anchor, BMB Fasteners, or Champion? So here, order makes no sense, okay? Here, order makes sense. Here's a categorical factor for you, grade of stainless steel. Well, it turns out you could potentially order these. These steels have different hardness properties. They have different malleability properties. They have different corrosion resistance properties. They have different cost properties. But generally, you would treat this as a categorical factor, okay? This would be a discrete numeric again. They only sell bolts in certain sizes. I mean, in theory, if my range is 7 to 10, I could specially manufacture an 8.5. But would I do that? Probably not. I'd probably just buy the 8 and use that. Wouldn't be right in the middle. If my range is 10 to 16, once again, they don't sell a 13. But I could use a 12 or a 14, or both of them as as midpoints in my range. We'll talk a little bit about mixtures, but I'll bet almost everybody, if they haven't done it themselves, they've watched their partner, blend salad dressing. You know, the bottle even has the line for the V, the W, and the O, okay? Well, whether you're making an 8-ounce cruet or 4 gallons in a jug, it's the proportions of the ingredients that affect the texture, the taste, okay? So we'll have some examples with mixture variables. And I got a separate page that it's now a Word document. It's about 4 pages long of different recordings. So again, I've picked up the pace here, but you can see I have all sorts of recordings that you can easily get to on these topics. I happen to be highlighting the mixture one there, but lots of different recordings available on doing these types of designs. Blocking factors, things like day or batch. We don't think it should make a difference, but what if it does? The way to check is to do some testing, in this case, a design run over 5 days. Well, what if it's sensitive to humidity? And so Thursday's the one rainy day this week. Is that what caused the problem? Well, what we don't know is, what if because it rained, Jim was unable to get into the lab to do the testing that day, and I had to do it that day? Well, maybe I don't run the equipment quite as well as Jim does, okay? So is that the reason? The point is, if you don't block, you can't test if the process is shifted for that group, okay? And so blocking, it's a relatively inexpensive insurance policy. It's only one more trial for each level of your blocking factor. Okay, here's a comparison of a couple of classic designs, what we're going to be doing with optimal designs, and the number of terms in the quadratic model. So this is for all continuous factors. You can see the red circles kind of go up monotonically. The classic designs kind of jump around, and that's because they're built on symmetry, but they're almost always bigger than the green line, which is where, and this is the default setting in JMP, we always build a design 6 trials bigger than there are terms in the model. That gives us 6 degrees of freedom for estimating model error. What you should see is that the designs, once you get past 4, and really by 5, or I should say by 6, the classic designs start to get really big. And I'll even call them bloated. Okay, and we're going to see some more if we get into comparison designs. We can even look at some charts comparing where the points are. The point here is, with custom design, you could probably start to look at more factors. And when you do that, you start to look at more interactions. If you're always at 3 or 4 factors, you're looking at 3 or 6 interactions. You get up to 6 factors, now you're up to 15 interactions. So you're opening that door to getting a little more understanding of your process. The other thing we're going to show later, if you've done a screening design, rather than starting over, if you're not going to change the ranges of the factors you're keeping, you can just augment the screening design with a small set and turn it into a response surface. So that black star is showing you a 10-factor definitive screening design. It was unclear which of the factors, there were like 6 that looked like they were important, but it was unclear, what were the final model. So you could augment it in those 6 factors, and it turns out it was only 2 bigger than if you'd have known the right 6 at the start. So you can even do this sort of sequential experimentation that way. Okay. Let's move things along here. I think I'll come back to this topic later where we do comparisons of designs. The short answer is these eye-optimal designs are very often a very strong performer for things like power and fraction design space plots. So what fraction design space is saying, what's the minimum predicted variance across the design space? So lower and flatter is better. And you'll see that the best one on this list is the eye-optimal, but the second best is a smaller eye-optimal. So you could actually save trials and still do better by these statistical criteria than you might with some classic designs. Okay, we're finally going to make a design. So this is the example I highlighted before. We've got 3 responses, 4 factors, and this is kind of what all the different parts look like, but if I were to make this from scratch, I'll go out and show that now. So let me get out of this and find JMP here. So if I were to do this from scratch, we would go to custom design, and we would put our responses in. So up here I can even give goals. So I wanted to maximize the speed, I want to maximize the contrast, I want to minimize the cost. So I'll just type them in. Except that I didn't get it. Now, the good news for those of you watching me type here is at any point in this process, I'm now going to add 4 factors. They're all continuous. And again, I can put in their names. The range is, by default, they're -1 to 1. We call that coded. But I generally, if you have the actual settings, it's better to put those in. That one's also 50 to 90. Now, I don't know, it took me a minute to type it in. If you think you're going to test a bunch of designs, at this point, it's not a bad idea to save the factors, and you can even save your responses. Okay, so I've got these other 2 files open. So now, if I wanted to do another design, I could just go into DOE here and pick, let's just say I went to do a definitive screening design with this particular set of factors. If I pick this, I'll always have that option of, you know what, just load those factors in. Okay, so you're not constantly retyping and retyping and retyping. But at least once I wanted you to see me type it. Okay, so we've got it all filled in here. Let's get back to here. And we click continue. And we're not doing constraints yet. We're going to come back to that. But here's where, if my goal is I want a response surface model, it's a 1-button click. You could get there by adding first the interactions and then adding the powers. But 1 button will get us, we'll add both of those at the same time. So if I make this long enough, you can see that okay, so what I'm highlighting are the top 4 are my main effects. The 4 white ones are the squared terms, and the 6 other interspersed blue ones are all the pairwise interactions. Okay, so that all happened with 1 click with RSM. So down here, the smallest design you could run would be 15 trials, because there's 15 terms in the model. Okay, why does it take 2 points to get a straight line? Equation for a straight line is y = mx plus b. We all had that back in high school. Well, it's a 15-term model. You got to have at least 15 trials. By default, JMP wants to do 6 more. It gives us those 6 degrees of freedom for model error. And so now I could click Make Design. And there's a 21 unique trial design. I'll click Make Table. And you know, there it is. I would need to now go and collect data. So one of the things I think I can do here, if I copy this off, is let me open up a this file here. It turns out they said that happened intermittently. Let's hope it's still intermittent. There's a gentleman in the back that's handling that. Okay. Whoops. Okay. So one of the things I just did there was I've actually got a formula in these columns. So if I paste in these settings, these are, every time I do it, I get a slightly different answer for the responses here. So this is a simulator that I could then go back to where here's my design. You know, you would now have to go out and physically run your experiments. Well, now I'm coming back and pasting that in, except that that's not what I wanted to copy. I didn't succeed at getting what I wanted to copy. Let's skip that step. So the point is we were able to make the design. We'd have to go run it, collect the data, and come back, and then we would be able to analyze it. So that went kind of quickly, but get back to the slides on that. Okay, so we put all that information in, generated the design. Now, one of the things I could have done was I could have added replicates. Why do we do replicates, anybody? What was that? Well, one is to estimate noise, okay? A lot of times we're trying to, if the power isn't that high, we need additional data. So we'll often do replication for that, okay? The default in JMP will replicate mostly corners of the design because those points have more leverage for the model. You can force the replicates to be center points, okay, which is sort of what people did historically, but the center point has the least leverage for the model. So in that sense, you know, you have to make a decision which way to go. I generally prefer my replicates in the corner. That's not to say I haven't had replicates in the center. That would be something where, particularly if you want to control, you might run that center point every few runs. And that way, when you're done, say you had a total of 30 experiments, and every third one was that center point, you'd have a way of detecting trends in your data. And so again, one of the examples I can give of that is out at Dugway Proving Ground, if you're doing testing in a breeze tunnel out in the desert, the temperature in the morning and the temperature in the afternoon, it may swing 40 degrees. Well, if the temperature is affecting your experiment, it would be nice to have some validation of that, even though temperature isn't in the design. You might do that with a replicated center point. Okay. I realize it went dark behind me. We're going to move to a more complicated problem. If my screen is visible. There we go. So now we're getting back to sort of the real world side of things. I've got 4 different factors. There's 3 different types. So I've got continuous, I've got discrete numeric, I've got categorical, and I've got one of my factors hard to change. And at the high combinations, I can burn the product, and at the low, it might not cook enough. So what might I have done here historically? Well, I might have gone and said, you know, I can fit a square right about there, so I have to shrink my ranges on my time and temperature in order to make the design not fail in the corners. So we'll do this a second time where we don't know the constraints, and we'll actually break the design on purpose and then repair the design by taking the ones that worked and then adding these constraints onto it. So let me go out. This comment here on the, let me talk about how the constraints work. So again, you know, if you're in the pizza business, anybody ever been in the pizza business? You're the resident expert here. When do you make your money? Every evening in a few hours. You know, pretty much people aren't ordering pizza at 10 a.m., you know? So you need to make those pizzas as fast as you can because your oven can only, a lot of these belt oven ones, only so many pizzas can go through in an hour. So you need to make sure that you can make as many pizzas in that time frame. So we want to put these constraints in. Where did the constraints come from? Subject matter expertise. Somebody knows, you know, too high a combination of time and temperature will burn it and too low won't cook it. So we'll have a place to put the constraints in, and there's some numbers in those boxes. There's 10s and 1s and a 600 and a 500. Where do those come from? You can figure all this out geometrically. You can use algebra. You can put the numbers into JMP. But this, again, to give you a picture of the process, the blue square is where we're thinking of experimenting. If you extend those lines all the way back to where your x-axis is 0, I don't know if you guys remember these terms, you know, at the abscissa and the ordinate, you know, but where you hit the vertical axis is the intercept. And the slope is the rise over the run. Does anybody remember any of this? Okay. It's longer ago for me than it should be for you. So we know the slope is a -10, and we know the intercept for the top line is 600 and the intercept for the bottom line is 500. Or you could put the coordinates of the points into JMP and say, can you find the equation of the line for me? And it'll do that. And so you'll notice down below it's got the intercept at 500 and the time slope there, it says -10. So either way you do that, we can put them in. But there's a problem as you keep constraining and constraining. And if you think about this, what happens as those two lines get closer and closer together? I'm getting a bit higher and higher correlation between the time and the temperature. If you have a diagonal line, we're back to, sort of the problem of I can't tell you if it's time or temperature. So I picked the red case here as kind of a slightly broadened design, but that's what we're going to want to input into JMP when we actually make this design. So once again, that's what it's going to look like when we have it all filled in, and hopefully you understand where the numbers come from for the constraint. And so we'll go off and make this design. So let me escape this. And I think under pizza factors, I have, you can see here a table. This is where I have saved these factors previously, so you don't have to watch me type it in. So if that is the active window, and I go to custom design, I can just say load the factors. And now you can see that my time is continuous and easy to change. My temperature is continuous and easy to change. But I think we wanted to make that hard. So I will click on the easy and change that to hard to change. Okay. My pizza size are 9, 12, 14, and 16 because those are the available pizza pans. It's got personal, small, medium, large. And now I've got 3 different types of pizza: cheese, veggie, and meat. So I've got my factors in. I now need to add my constraints. So I'm going to specify, in this case, linear constraints. And I'm going to add 2 of them. And so it turned out it was 10 times the time, 1 times the temperature. One of these was less than 625, and the other was 10, 1, and I need to flip this inequality constraint to 475. Now, if I've done that right, it should match what we have here. Okay, so I've managed to get, so if we again look here, I'll make that large. Okay, so I changed this to hard, but I imported everything else. I added these 2 inequality constraints. I went through kind of the geometric drawing solution as well as the algebraic solution. And we're now all set to go, except that right now the model is just main effects. So notice down here the minimum number is 6. I want, again, to use a response surface model. So when I change that, this now went up to 17. And right here it says number of whole plots. I'm going to change that to 6. And you'll notice this number is now divisible by 6. So there are 6 groups of 4 tests that are all going to be at the same hard-to-change factor temperature. Okay? And we shouldn't get any in the upper high corner or the lower low corner. And it's going to support a response surface model. So if all of that is set, this is where we specified sort of our real world. We click Make Design. And I'll just make the table for it. And again, Jim pointed out there are some graphs at the top. So notice here, if I click the little graph icon, I can actually see here, if I click on 1, 3, and 5 up top, I've selected each of the whole plots. And you can see the temperature within each of those whole plots is all the same. Okay, so they're randomized within each set of 4. And, you know, in this case, the temperatures they're pretty widely different. So you'd have to wait between 425 to cool down to 350, then you'd have to crank it up to 450. Sometimes when you do this, you get 2 numbers that are real close together. You can just redo it again. That's just the randomization happening. But there's an example of the design. And now you can visualize this lots of different ways. I could go back out and do a distribution of all of these things, where again, in this, I can, when I click on anything, it shows me where that is selected. So notice when I pick whole plot 6, that was the group around 380 degrees. And if I pick, you know, the cheese pizzas, you can see how they're spread out across all the other variables. And the same is true of veggie and meats. And if I pick something at the high time, again, it's across all, you know, the low and the high pizza size. It's evenly proportioned across the meat. So this is a way to visualize the design. Let me also show you if you did maybe a graph builder here on the time and temperature. So I think the time was down here and the temperature was here. Okay, what you should notice is that if I get in here, I'm going across, nothing in that upper right, nothing in that lower left, because again, I said avoid that time and temperature. Now, if I bring the pizza type in, I might want to color by that. And unfortunately, I don't like blue cheese, so I'm going to change that to yellow. And my veggies are red. They think they should be green. And my meats, I'm okay with that being red. Okay, so, but at this point, one way you could get what are the sizes for those pizzas, I could come over here to pizza size, right-click on it and say, why don't we use that for the marker? And now when I come back to this graph, I'll make the graph maybe larger here. And let me go to marker size. So, sorry about that. Get out here, we'll do it at the table level. Well, not there, hang on. Just trying to change my marker size. A little more readable. But now you can see where the distribution of the different colored types of pizza are and the different sizes. And you can even say, you know, what if I wanted to, you know, wrap this by the different pizza sizes? I can put them all in their own box. I could have also wrapped it or overlaid, wrap it here by the different cheese types or pizza types. So anyway, there is I'll call it real world DOE, where we've put in all the hard to change and constraints information, and we got our 6 different whole plots, and looked at different visualizations. The 2 I didn't do, I won't take the time. I could have made a 3D scatter plot or a scatter plot matrix, which also would still show the constraints in the regions. Okay. I think with that, I think I'm just going to get off stage and let Jim get back up here. Do we have any questions on real-world design? We're going to come back and fix a broken design a little later. Is that right?
Yes.
Okay.
So as transitioning here, we do have our session at 3 with Brad. So I've got 2 questions up so far. One is to kind of talk about the current and future state of DOE and where he sees research going. And the other is that John had asked is, you know, well, okay, I got it. I'm all in on this log linear variance stuff. So I Steve alike. How would I set up a design so that I can optimize my results for log linear variance? I don't know, but Brad might. Anything else that I should put up there for Brad? Based on maybe what you saw, Tom, or just in general?
Just
So in the custom, can you put, it's a random effect up front as you build? It doesn't know that. That's more the analysis platform. So it seems like if you know that you're going down the random world, you should take that into account with your covariance and information matrix.
That'd be a good Brad question.
Yeah, I like it. And in terms of design for time to kill, some of those designs for reliability. I'm trying to think of a guy from Arizona State. It was Connie Bohr and Ron Fan wrote some papers on DOE for reliability. So let's see, the question was designs for random effects or mixed models. And that's a great question because we too often assume everything is fixed, right? When in fact it's not. That really we should be doing a lot more mixed models. All right, off we go. And so Tom did mention that there's this thing that's called a hard to change factor. So we're going to talk a little bit more about what exactly this hard to change factor does for us, to us, kind of a thing. And those are called split plot designs. So if you have a hard to change factor, it's a split plot design, which right away you are violating one of the 3 R's, right? The foundations of design of experiments. There's the 3 R's: randomization, replication, and blocking. So you have not randomized appropriately when you have a hard to change factor, right? Your hard to change means that I'm not going to randomize completely. So there are penalties to that. So Sir Ronald Fisher turning over in his grave is one of those, and we have to make sure that we can tidy up, if you will, our sin of not completely randomizing. So that's what a split plot design is doing. But we honestly, to Tom's theme, is we don't want to be the academic in the room that is telling us you have to randomize, have to, right? We have to be sensitive to the test program. So if it turns out that it would make sense for people, for your test program to not randomize, and you've done due diligence and thought through it and justified it, then yes, we can accommodate that as a split plot design. So that is some of the maybe the criticisms of using a custom design type thing, is that people that really don't know what they're doing will say, yeah, I'm just going to make this hard to change because honestly, you know, it'd be better just to run it this way. And a lot of people kind of do that anyways, right? That you spent all this time coming up with a fantastic design, and then you give it to the team to run, and they kind of do it their own way. They're like, no, that's too hard. We need to do all these low altitude or low temperature ones first. So ultimately, you fall into a split plot world, and split plot can, at the outset, it can be designed in, or you can do your analysis of your data as a split plot design. Even though you designed it as a completely randomized design, it may not have been run as such. So you then would then flex and say, okay, I need to actually kind of make these guys whole plots and what we'll call random effects that we've already talked about. So Navy corrosion testing, I've been working a lot in that lately. We're doing additive manufacturing for the Navy, so rather than subtracting and making stuff out of big hunks of metal, we do 3D printing and start from some powder and make it into a magic piece of steel in the right shape. And there's a lot of ramifications to that. We have to make sure that it is corrosion resistant. Tom showed there's some 316 stainless steel out there. We're working with that. So corrosion, we'll talk a little bit about corrosion because I think we called this like with case studies or something. So I'm trying to pepper in a couple, hey, actually we do use these things. And then, of course, the classic Neil Young, Rust Never Sleeps, right? It's kind of a great, I think it's a great album, but it's also a great saying. So talking about random effects, probably the best way to think of it is this kind of the bottom here is if you have two operators and there are exactly two operators, then that is a fixed effect. But if these two operators are a random sample from your group of many, then that should be a random effect. And I suspect that many of us have committed that sin that we just have operator as a fixed effect, when in fact it really should be a random effect, right? So is it, pilot 1, pilot 2? Are those the only pilots that will ever fly? Or is it truly a random effect? So again, the 3 R's right there, we violate it. So hence we have this hard to change thing. So split plot, not surprisingly, comes from the agriculture world, from Sir Ronald Fisher. So he was doing this back in the day in in fact, I want to say that next year we should do a short course on split plots because it will be the 100th anniversary of them. So, which I guess is Stu Hunter's older by 1 year, maybe, right? So anyway, the idea with the split plot is that you cannot randomize. So if we think of a field there and we have maybe you have two factors. One is going to be your irrigation method, and the other is going to be your fertilizer quantity or type. You can easily do the fertilizer randomization, but on a field, you pretty much are stuck with how you're going to irrigate it. So you can't really randomize that, but you can randomize within that field. So that's where the idea of this split plot comes up. And by the way, you'll see that note on the bottom is the paper from Brad Jones, which is right here. Okay, maybe that's the end of it, but this is it right here. The split plot designs, what, why, how. Great paper that if you did the Google right now and type in something like Jones, what, why, split plot, it'll come up to a website from Taylor and Francis, and you download it for free. So you can have this right now. So don't say I never gave you nothing, right? So you get a free paper from Brad, and heck, we might even be able to arrange a signing of it. Actually, Brad is, I never miss the opportunity to throw Brad under the bus when I'm teaching, so I'll throw him under the bus here as well. It's like he's a pretty proud guy, so I'm sure he'd enjoy signing that for you. So in any event, what we talk about this split plot design is we have to put these hard to change factors are the whole plots, and then the easy to change, we randomize within those, as Tom mentioned. So the idea is we do have some randomization going on, but we have some restriction in the randomization, and that's going to be the whole plots. So if you have a single variable, then you have the whole plot associated with that, but you could have more than one variable that's hard to change, so your whole plot would be the combination of the two variables, kind of a thing. So, and then you got the whole plot whole plot, and then you got the subplot, or what might be better called a split plot, since we're doing split plot designs, right? So this is kind of their takeaway of, what the bottom line is with a split plot is really blocks, but these blocks we kind of care about, right? Because as we mentioned, the 3 R's, randomization, replication, and blocking, right? So blocking, typically we know that these are influential pieces to our experiment, but we don't necessarily care about them. We just want to account for them. Different from that idea is what happens when we want to account for this. So temperature or irrigation method, whatever it happens to be, we need a way to account for that split plot. So we could do the time, rate, temperature. So the idea here is that you could see this has temperature and rate are both hard to change. So we have 4 different whole plots in there and in the full factorial of those guys. But within the subplot of time and angle, those can be randomly assigned, okay? So whole plot 1 is when temperature's at 35, rates at 4, and then we've got the subplots within there that's going to be the full factorial. And it builds and so forth. So then ultimately, here's your design where you can see that the circles are the whole plots where nothing changes between temperature and rate. Why? Because it's hard to change. But time and angle, you can see that they're random in terms of, if you look at the pattern for the top, red circle, and then the middle two red circles and the last red circle, they're not the same. You can they're completely free and should be randomized as much as possible. So here's another great paper on split plot designs from Scott Kowalski and Pete Parker and Jeff Vining. Is Pete around? He should be here somewhere. I think he's got a talk tomorrow, but Pete is a great friend of DataWorks. I think he's one of the founding members, if you will, but also a really bright guy. And very interesting. If you run into Pete, you need to chat with him. He's a very interesting guy, kind of has a self-sufficient farm down in Virginia, but also amazingly accomplished in split plot design. So anything that between Tom, me, and Brad can't answer, Pete's got it tomorrow. So just let him know. But what I want to do is I want to show you this plastic example here. So the idea is this is they're trying to make some injection molding, I think, here, where, of course, temperature is the one that's hard to change, and they have this data here for us. So here's the important part. The takeaway is, why do you go through the pain and suffering of doing a split plot design in terms of the analysis? We know why you set up the design, because you want to be much more efficient and not have to change. But in the analysis, can't I just waive that whole random effect stuff and mixed modeling and put it aside? Not really, because you could get two different answers. So, for example, on the left, we're going to see what is statistically significant here is temperature and then time by temperature by rate. On the right, you'll see when you do it correctly, the correct factors are temperature is actually not statistically significant. And these bottom three are statistically significant. You can see that this two-factor temperature by time is marginally so. But here's what I want you to focus in on, is look at the standard error. Do you see that the standard error is the same for all of them? Do you remember I showed you at the beginning, when I showed you the Oriole, the Commander, and all that the standard errors, or the confidence intervals were the same? And then I said, that's not really right. That's the same thing going on here, is we need to appropriately account for the variance structure. When you do the split plot design, you have a whole plot error that's not appropriately accounted for here. So if you look up in this world here, let me see if I can, does this show up? Oh yeah. So if I look at these guys up here, you'll note that the standard error for temperature is much higher. It's 1.3 versus 0.71. So you're paying a much bigger penalty. So think about the ramifications of this, is you are often going to make an error in thinking that effect is active when it truly is not. Okay, so my process here is relatively robust to temperature, despite what the classic version told me. Here, I think temperature is pretty darn important. But if you come up with the correct estimate of error, you'll see that it's not really. Also, look below. Do you see that these the standard error for the factors that are not hard to change, they're actually lower, rather than the 0.7 blanket that we got over here? So now I'm my signal, everything's signal to noise in our world, right? So now that noise is appropriately estimated for those easy to change factors, now I can figure out which factors are statistically significant. And overall, my R square is, appreciably better as well. So yeah, it makes a difference. As much as it would be great if it was just, it's all about the same. It's all signal and noise, and if the signal's high enough, you're good to go. Not really. You really want to maybe do some extra step and do the split plot analysis. And also do this when Tom's going to talk about repairing broken designs. A classic example of the broken design is that you have not run it the way it was supposed to be run, and then you're going to have to analyze it as a split plot, or perhaps just use it as a block. So let's take a look at this in here. Yeah, so we're good to go. So let's go ahead and take a look at, well, how do I do this? And I know that some of you said that you are interested in the split plot design. So actually, let me do this. Let me clean up here. I'm going to do close all but this, save none, back in the journal. All right, so I am here under 1.4, where we have restrictions on randomization. So let's look at this plastic model. So I've got my 4 factors, and I know that temperature is the hard to change. So if I come under DOE, and I do my custom design, and I'm going to load those factors in here, and I note right here that this is it. So as I mentioned, the criticism of the custom designer is that people that aren't as familiar, and honestly, most of the people we work with that are using the software are not, like Tom, they're not statisticians, though Tom certainly has passed all of his statistics qualifiers. But a lot of people haven't passed the qualifiers and would just say, oh, I just want to make it easy or hard to change so that I don't have so many things going on for convenience. You really don't want to do that unless you have to. So, but that's all it takes, is you just flipping this switch right here to hard, and now you're talking variance components and things like that. So in this particular case, maybe we would like to look at some interactions, second order interactions. So if I look at that what Scott had done over here, Scott and Jeff Vining, let's see, where was their design? Here it is right here. So they've got a 32-run design. I know that because the total degrees of freedom is 31. So they've got a 32-run design, and they've got 4 whole plots, meaning they only have to change the temperature 4 times, and or 3 times for that matter, or actually they could get lucky, right? And if you look at it, they did, that 2 and 3 end up being both at the low level for temperature. So they really only have to change the temperature after the initial one. They have to change it twice. So that could be good. Of course, you could maybe cheat, right? And then do a real super split plot by saying, well, my random, rather than going 3 being at the high and then 4 being at the low, you could always kind of unrandomize it. Don't recommend it. So what we want is 4 split plots. So I'm going to come over here, 4 whole plots, and that's where I put this 4 in here, and we do want 32 of these runs. So now I go ahead and I make this design, and it'll probably take about 15 seconds or so, and I'll show you what the power is. So here's the problem, is because I'm not randomizing and I'm not changing temperature much, that's going to hurt me in the power, okay? In fact, if I look at my power analysis right now, I can see 32 runs typically in DOE is enough that you don't really have to worry about power, that you're able to get your 100% power. And for those that aren't familiar with the JMP interface here for power, what this is saying is if I assume a noise of 1 and my coefficient here is 1, then that means it's a 2 standard deviation shift in the response. Why? Because we're looking at -1 is the low level and then +1 is the high level. So you're really going 2 steps. Because a coefficient, if you think about a slope, is for every unit change in it, what happens to the response? Well, here we're actually taking 2 changes. So that's why I'm really looking at, this is the power to detect a 2 standard deviation shift in a split plot model is only 20%, despite having 32 runs. Now, a way to fix that is if I go back here, and instead of doing 4, I do 8 whole plots. So you don't have to have it all work out geometrically, but it's better if you can. So in other words, 32 divided by 8 is 4, and that's kind of a good number. So you may not want 5 whole plots here because it won't flow through as nicely. But you don't have to. JMP will figure it. You tell it how many you want, it'll give you that. So if you want 7, 5, it's fine. But generally, it makes sense to try to keep it some sort of a multiple of. So now if I make this design, we'll see how the power changes. Why? Because now I'm changing the temperature 8 times, or whatever, 7, or perhaps even 5 or 6, depending upon what my randomness is here. So now I've got this guy, and I can see that my power has creeped up, quite a bit. So one thing, maybe off topic here, but I think maybe in DoD, NASA world, is it somewhat a default of 80% power to detect a 2 standard deviation shift? Is that maybe absent anything else? That's what maybe somebody who signs off test plans and temps and things like that is looking for. So, but at the end of the day, often our signal noise ratio is well greater than that, right? So even though I've only got to detect the 2 standard deviation shift here, what happens if I'm looking at maybe a 3 standard deviation shift, right? So temperature 1.5, and now we can see that we're at 90% to detect a 3 standard deviation shift. So, in any event, we can play these games, and you also could say, a real model isn't necessarily going to have all of these factors statistically significant. So you can look at what a reduced model would look like, say maybe 3 main effects and 2 two-factor interactions, and then see what the power is. So that's how you create the design. So it's relatively straightforward, and JMP is doing the work for you, right? So we created this design, and then we can look at this color map on correlations and see that it treated me pretty well, right? So even though I've kind of done this restriction on randomization, I'll go ahead and create this design, and I am ready to go. And you'll note that there are, in fact, 8 of the whole plots, okay? And I didn't get, well, I guess I got kind of lucky. That you want to have some runs together, right? Because that means you don't have to change it, kind of a thing. So
I would say that I don't think that's good advice to people.
I'm just saying it's if you're lucky.
But I think the idea is if you have a factor, you want, and it's going to happen twice in a row, you should go in there between those 2 and set it to something else and bring it back. Because what you're trying to capture is the randomness of someone setting the temperature. And so if you leave it 2 in a row, you kind of are defeating the purpose.
I don't disagree at all.
Okay.
Yeah, because I guess what we're already talking that we're in this world, and it could be even a default, right? That your software by default should have them every other time. Ask Brad, like, hey, why wouldn't we want to change that every other time? By default, because.
And it's not truly random.
But you've already, committed the sin, right? So in any event, how do you do the analysis? So the analysis, we have this no kidding data all ready to take a look at. So let's come under our journal here, and this is going to be our plastic manufacturing split plot. So now I've got this is the original, by the way. So I made the 8 whole plot design that we just looked at. Now the original that was actually done in the paper, they only change it 4 times. So now we know that our power is kind of light in terms of the temperature variable here. So in order to do the analysis, you come under your analyze and you fit model, and what you'll note is that it already is loaded, because JMP knows that you created this design as a hard to change, hence a split plot design. It says, okay, I'm going to go ahead and make this whole plot a random effect. So it's already put in there as a random effect. And then you have the rest that you asked for, right? So when you built the design, you said, I wanted these main effects and these two-factor interactions. So what has happened is you've talked yourself into a new estimation method for your parameters. Previously, you could use standard least squares, which would be the ordinary least squares. X prime x inverse x prime y is how you get your betas. Not so anymore, because your covariance matrix has changed, right? Remember I said now you've got two estimates of error, so now we have to use this guy right here, the restricted maximum likelihood. There is also the EMS version. Anybody an EMS person? Yeah, the expected mean squares. So like if you look at a classic book like by Douglas Montgomery, and you look at how he brings up split plots, he does a lot of algebraic motivation as to how do I actually estimate these variance components and things like that. And it's all based on expected mean squares. So that is kind of the traditional way that it's been done. But REML is kind of the recommended way. In fact, I don't know, Tom, correct me if I'm wrong. Anytime in JMP or elsewhere you see REML or maximum likelihood, jump on it. It's good stuff. Is that maybe a fair? Yeah. So a lot of times you'll see, in particular, like the walled interval versus the max likelihood interval. Go for the max likelihood. So the walled is like a normal approximation that's very computationally efficient, but not necessarily as good as a max likelihood estimator. So, but when we have computers that have, i9 processors and, 64 gig of RAM, you're probably okay letting JMP do the heavy work to get those max likelihood estimates for your 16-run design. So now I'll go ahead and I can run this. You see that there's the unbounded variance components that are in there, that you have that option. So some people are uncomfortable with variance components that are negative. It happens. So you can kind of control that there. So same interface here. You'll go ahead and remove your insignificant effects. I'll maybe do one more, and we'll run with this. So now what I've got is I've got my parameter estimates here, but what's new for me is the REML. Right, so I've got my REML, my variance component estimate there. So I've got my whole plot, and the variance ratio is this ratio right here of my whole plot error, okay, to the regular mean squared error, just like you would in an everyday world. So what that ratio is, it's going to be this guy right here. So 5.78 divided by the 9.9. That's going to be the variance ratio. And then I do get a p-value that kind of says, well, do I have an effect due to the whole plot or not, kind of a thing. So we can kind of see right here, as we looked at these are our BLUPs, our best linear unbiased predictors. So that is essentially, if you just took the average of that whole plot, that's what your best linear unbiased predictor would be. So ultimately now, we do have, let me see, back up here is where we can take a look at these parameter estimates and note that this guy came through as much higher because it has two sources of error, right? The penalty for not randomizing as well as the regular mean squared error. And then you can have your means test, and like any other idea in here, you can do your factor profiling kind of a thing, and you see that you do have a fair amount of variability in there. That is the example for the 32 run. There's even another paper in Quality Quandaries from George Box, who's kind of one of our heroes, right, our DOE heroes. And he had kind of the same idea going on where he wanted to prove that, hey, it makes a difference. And that's the world famous corrosion design paper. So if I look at the corrosion design here, what you'll note is it's going to be a 24-run design, okay? And it turns out that temperature, of all things, is hard to change. So, by the way, temperature is not the only thing that's hard to change. There's probably a lot of other factors in your experiments that are going to be hard to change. But in this case, we have 3 levels of temperature and 3 coating processes, and then we can go ahead and make this design, and then we'll see how to analyze it and recognize that, you once again aren't getting the same important factors if you do it the classical way. So the word to the wise is, if nothing else, at least look at what you are getting when you do the split plot analysis, and then if it looks like it's similar enough to your ordinary least squares and you really, really want to use them, then maybe, but try to stick to the cleanliness of the stats. So in this particular case, we had the hard to change factor was the temperature, and we can see that is, again, only 20% power for these 24 runs. So if I go ahead and then just looking at that color map on correlation, we do have a nice clean orthogonal design. So by having hard to change doesn't necessarily mean that you're hurting your correlation structure, kind of a thing. So now if I make the table, we look at this pattern once again. We see right here are my whole plots where we don't change the temperature at all, right? So we asked for 6 of them, which kind of made sense. Why? Because we had 2 temperatures and we got, 4 different coatings. So we're able to, that all kind of makes sense. It's your number of runs, right, divided by the different levels within there. So what I've done is for every whole plot, I'm able to have every coating within that. Doesn't have to be, but it sure cleans things up if you can. So, for example, if you could only change the temperature 3 times, then that would be a much more difficult design to accommodate. So let's see what George's message was for us. So George will bring up his no kidding data, and that's going to be this guy right here, box split plot corrosion. This has the data in it. So we'll go ahead and fit it the wrong way. So I'll do analyze, fit model, and the wrong way is just taking out the whole plot, right? So if I remove that, so now I have just my 2 factors and my 2-factor interaction. So I can go ahead and run that. And I can see that, it looks like as I reduce this model, it's really temperature is the only thing that makes a difference, okay, as I reduce that model. Now if I do it the correct way, I select model again, and I have the whole plots random, and I run. It appears that the furnace temperature by coating 2-factor interaction is statistically significant, as well as the coating, and then maybe not so much the temperature, but the temperature is involved in that interaction, so we need, by heredity, to leave it in. So again, very different results, and it all comes down to, we now have, when I look at my parameter estimates here, you'll note that we have a different standard error estimate for your coating as you do. Look at your standard error and the temperature. It's 20. So we have, rather than just one that satisfies all, we have the correct standard error measures. Split plot designs. Questions for Tom, Brad, or me? Or you're saving them the hard ones for Pete Parker? So the takeaway is that these are probably showing up more often than you think. And you should see what happens as you analyze it correctly, right? So knowing that you maybe had a restriction on randomization that you didn't realize. Repair and designs, Tom? Is that our next?
Sure. That'll probably take us to lunch.
Yeah, and then after lunch, we'll do some different types of designs, mixture designs, screening designs.